Hello and welcome to TidyX episode 173. TidyX is a screencast where we go through and explain how our code works. My name's Ellis Hughes.
My name's Patrick Ward, episode 173. Thanks as always for joining us. As always, like and subscribe on the YouTube channel. Questions, comments down below. If you'd like to donate to the show because you feel like it's helped you and you like us and we're nice people, we do have
You
a
want to get us a
Patreon
beer?
page. Yeah, we do have a Patreon page, and we're always grateful for anything that you may choose to donate. That said, episode 173, we're continuing our What Can I Learn in 20 Minutes series, and we're extending last week's episode where we built a simple, little logistic regression model trying to
We're cheating a little bit since we're branching off of last week.
Yeah,
But you can learn all of what you need to learn to apply Bayes
yeah.
in 20 minutes here.
Yeah, so we'll try and extend last week's episode, which was on estimating the probability of a pitcher getting into the Hall of Fame, which is a very low occurrence event, as we talked about last week. We built a logistic regression model. This week, we're going to extend that to a Bayesian model so that we can talk a little bit about how to estimate uncertainty. So all of this data pre-processing stuff is from episode 172. So we can skip that. If you're interested more in the data pre-processing, check out episode 172.
There'll be a link appearing here. Okay,
And
cool.
here we are, episode 173.
Let's do this. All right, so there's a number of packages that we need to load up for us to apply Bayes. So first there's the library rstanarm. Then there's Bayes plot, TidyBayes, and broom mix. And all of these different packages will allow us to either run a model, I believe that's rstanarm, Bayes plot allow us to view, TidyBayes allow us to do some data manipulation, and broom mix is to pull out the final models in a nice pretty way. So it's easier to work with. So let's load all of those. Let's also make sure I've loaded up library tidyverse and lawman, because that would be a real shame if I got further on and forgot to load a library like I have before. What? So let's fit the model. Patrick, how does this model work? What's going on here?
So the model is the exact same as the model we did last week, where we fit a logistic regression. This time the function is stan GLM, stan generalized linear model. So that's the wrapper function that rstanarm provides us. Basically what it's going to do is it takes the exact same syntax of our regression models in base R, and behind the scenes, under the hood, it's going to write a bunch of C+ code for us and convert that over to the stan coding language so that it can be compiled with a Markov chain Monte Carlo. So this is pretty easy to get off the ground. Everything here looks the same. We specify the model.
I need to load all the data from before.
We got to load the data.
All right, now we've got it. So now I can run it.
Specify the model. We load, we tell R where the data occurs. We say that it's a binomial outcome, so it's a true or false, or a 1 or 0, did or did not make the Hall. And we set the seed, because remember, it's a Markov chain Monte Carlo. So it's doing some simulation under the hood to build up from the ground, construct a distribution of the parameter estimates of this model. We don't specify any priors here. In 20 minutes, we're not able to get into like really going through how you would do that, but rstanarm protects you from yourself by using weakly informative priors. We've talked about this in the regression phase episode. So it does do priors for us. What we like about this model, though, is it's going to allow us to explore our uncertainty utilizing that Markov chain Monte Carlo, which is why we set the seed. So the model produces on default 4 chains. So 4 1,000 runs of 1,000 iterations of that Markov chain. And so we fit the model, it fit very fast, and we can take a look at the summary of the model as we would in normal logistic regression. So we can see right there, we get our model outputs. So we have our coefficients as well as their standard deviations, their median, absolute deviation, standard deviations, and their medians. We can also just look explicitly at the coefficients. And remember, it's a logistic regression model, so we are in log odds. So if we exponentiate back, to the normal scale, we get to odds, and we talked about interpreting these a little bit last week. And then
So
finally, if we
so let's
want to,
quickly say,
oh yeah,
what does this mean, just for folks that might have missed some prior episodes.
yeah, so we're on an odds scale right now. So for example, for every 1 unit increase in innings pitched, we see on average the odds of a player getting to the Hall of Fame being increased by 1.0013 times on a relative scale, right? So a little bit different than interpreting a linear model. We talked about interpreting these last week, but on a relative scale, that's what we see. So it's a very small amount because these guys are, often working on like, innings pitched is going to be in the hundreds over a season and then over a career. So really, if we wanted to interpret it, we could do like 1.0013 times, let's say like, 100 or something like that. And that would tell us the odds of making the Hall of Fame, or the relative odds of making the Hall of Fame go up by every 100 innings pitched. So if we multiplied that,
Mm-hmm.
we'd see that's change.
Yeah, just wanted to touch on that real quick.
Yep. Plotting, we can do a little bit of plotting or to help us interpret what happened with the model. So the first is we're plotting the actual 4 traces. So each of these 4 iterations had 1,000, or each of these 4 traces had 1,000 iterations. And so these are the fuzzy caterpillar plots. Basically, what we're trying to make sure and do is see that there's no real weird bias with any of these iterations. So we don't see the model going off, or the Markov chain going off in one direction or the other, or getting really, really tiny. We see that, there's some good mixing. There's some exploration of the priors, that the weakly informative priors that have been applied. Similarly, we can construct some density plots of each of these iterations. So this kind of just shows each chain with its 1,000 iterations and gives us a nice density plot to show us how these coefficients looked for each of the chains. So you could see, like, for IP outs, we could see the first chain had a lot more exploration. It was almost like this weird little bimodal blip. And then as the chains grew and grew and learned more from the data through each of those turns of that Markov chain, and they started to converge on something a little bit more normally distributed. There is still a little bit of bimodalness to this, and that's probably because we have relievers who pitch less innings than starters generally, because relievers come in select portions of the game, whereas starters are usually out there for the first 4 or 5 innings.
Mm-hmm.
And then the pairs plot is just a nice way to look at the coefficients of your model, so you can explore the correlated nature of those coefficients, as well as information about the distributions of them. So we put all 3 of our model coefficients, is what we said in the parameters.
Yeah. So
We just
MC,
wanted
MC
all 3 of
pairs,
the
fit Bayes, and then pars equals IP outs, SO, and R.
Yeah, so we can see that like IP outs and strikeouts seem to be pretty highly correlated with each other. There's a very large linear relationship, and then strikeouts and runs looks more like a kind of cloud of dust, and has been thrown onto the canvas, and we can see that they're all relatively normally distributed.
Mm-hmm.
And so that's a little bit about the actual model itself and kind of extracting out the coefficients. Of course, we know that these coefficients have uncertainty to them. That's the whole point of doing Bayes, is exploring our uncertainty. So we can grab that uncertainty by basically calling as data frame on the model. And what this is going to do is it produces 4,000 rows. So 1,000 iterations times 4 chains is 4,000 rows of possible coefficients that could have been derived from the observed data. So I tend to think of these as 4,000 different universes that could have occurred from our observed data. And so now we have this kind of like data frame where each column is representative of one of the coefficients in the model, including the intercept, and each row is representative of the possible 4,000 universes that could have occurred from our data. So this is a bit odd to look at. We can, of course, summarize these. Ellis, why don't you take us through some of the ways we could summarize what we're looking at here?
Let's do it. All right, so first we're going to set up par and set MF row to be 2 by 2. What this means is we're going to be able to plot two plots by two plots in a grid, basically. And we're going to look at the histograms of the various draws. So first we're going to do hist of the posterior IP outs. So in order to do that, we need to pull out the second column of post coefs, right? Because actually it's easier to look ahead. Second column right here. So we throw that into hist. Then for strikeouts, the third column, so this guy here. And then, of course, for runs, that's the fourth column. So if we throw that in, oh, wait, no, I've got to call par on that first.
Yep, there you go.
There we go. I know what I'm doing. So we can kind of look at how the distribution is and kind of trying to interpret what's going on with that. I think overall that looks like what we would expect. And then the next things we might want to do is actually investigating some of the values in the coefficients. So we use the apply function and set the input data set to be post coefs. We'll set the margin to be 2. What that says to apply is do this by column. So apply the function here to column by column, as opposed to if you set margin to 1, it does it row by row. So there's different ways you can apply. But here we're just saying, hey, calculate the mean across each column there. And the same idea with 126 here is apply it to the standard deviation. So we'll look at this, and this is basically like the summary of all the different models that we created here, saying the intercept on average is negative 5.6, IP outs is negative 0.00127, but there is, because this is Bayes, there's a standard deviation in all those models, so there's uncertainty in all of them.
And these are, what's returned there effectively is what we see in the model output for the coefficients and their standard deviations. In the Bayesian 20 minutes linear regression episode, we talked about how you could actually sample, let's say, 100 of the 4,000 universes or 500 of the 4,000 universes and build models using those 500 multiverse coefficients. And that's the interesting part about this is you could use all the information there, or you could sample and use some of the information and explore how the how the different universes might interact with each other and cross over, or some of our uncertainty in that. And that's the fun part about doing it like this is evaluating some of the chains and the iterations that are available to us.
What it found is exploring the world that is being shown. But we can also look at this in another way here. So we're going to take post coefs. We're going to pivot to be longer and take all the columns and put them down longer. We're going to group by the name because the coefficient name is now going to be a column as well. And we're going to reframe it and say, hey, we want the percentile of the 5%, 50%, and 95th percentiles. And we're going to use a quantile function on it. So it'll calculate the 5%, 50%, and 95% quantile for every single one of our coefficients. And then we're going to throw it into pivot wider to spread it back out again. And then we're going to throw it into cable here so it prints all nice like in our console. So we can see that IP outs, the mean IP outs coefficient was 0.00127, but the the fifth percentile is 0.0004, and the 95th percentile is 0.002. And so that's kind of that's trying to show you the range of the impact of IP outs on the prediction. Is how, if I'm interpreting it correctly.
It's the 95% plausible values for IP outs. Yeah.
Mm-hmm. And so it's that spread there.
Correct.
But we don't just want to look at what are the coefficients of the model. We actually want to try to make predictions with this. Like what is the result from our model? Not because we're not actually particularly caring in this case what is the effect of IP outs on whether to make the Hall of Fame. We want to know, are they making the Hall of Fame in this process here? So what we're going to do is we're going to take pitchers eligible stats Hall of Fame Sands 2018 final, which if you remember from last week is all the pitchers that we have all their data for and are no longer either got in or are no longer eligible to get into the Hall of Fame. That's why it's final, right? And now we can compare against a source of truth. So what we're going to do is we're going to select player ID, IP outs, strikeouts, runs, and inducted. So inducted being the source of truth. And we're going to calculate using predict the fit Bayes, so our fit model. We're going to drop in our new data set, and we're going to get set type equals response. And so that's going to give us the probability of this player getting into the Hall of Fame based on our model. And we're going to assign that to pred and inducted. So let's take a quick. You've already got it right here. So next we're going to do, we're going to take this, we're going to select the player ID, whether they were inducted. So again, source of truth, and pred inducted, what our model is predicting. We're going to arrange it by descending pred inducted, so the highest value of our model predicting down, and then take a head of 10 just so that we can look at it, because obviously there's a lot of players in this data set here. So we can look at that and we can compare what is our model predicting versus what actually happened, and kind of try to get an idea for quickly, is our model totally bonkers? Is it predicting somebody that there's no reason they should be? Or are there things that maybe are outside of our model that we can't capture here as to whether that's true or not? So let's take a look at this. Patrick, what are you seeing?
Well, the highest probability to be inducted is Roger Clemens, but he's kind of always been tied up to the steroid era, the performance enhancing
PED.
drug, PED era. So that's probably kind of blacklisted him with the voters. Other guys we see, Randy Johnson, Burt Blyleven. These were kind of historically dominant pitchers who obviously are in the Hall of Fame, and we had a high probability that they should be in the Hall of Fame based on stats alone. We see at number 7, Curt Schilling. Kind of, I think, wrapped up in the PEDs, also not generally beloved by the media in terms of his behavior. So there's a possibility that things that are outside of his statistical production are keeping him out of the Hall of Fame. And mainly these are things that we don't have data, at least in the data set that is provided. We don't have data that can be used as variables within a model to help explain that stuff. Like maybe, true or false did play, yes or no did play in the PED era, or 1 or 0 beloved by the public eye or not. Those
Yeah.
might be variables that weight heavily on these things.
Mm-hmm.
That's pretty cool. So what Ellis did was he made these nice little point estimate predictions, and that's what we did last week, and then we kind of stopped there. But the whole point of Bayes, if we're making decisions, is that we want to know about our uncertainty around these point estimates. And while, inductions into the Hall of Fame is a bit silly, I mean, who cares? It's point estimates versus uncertainty intervals and distributions. But if we're making decisions in something that maybe is more meaningful, like public policies or medicine, we probably want to know our uncertainty around these types of posterior distributions. We want to summarize that stuff. So rstanarm gives us some great scaffolding to do this. First things first, there's a lot of pitchers, so we're just going to sample 3 guys. Like we set our seed, we sample 3 guys, so the seed is set so that it's totally replicable for you guys. And here's our 3 pitchers. So we've got like a guy, these guys have all pitched relatively high amounts of numbers of times.
Yeah.
Let's use this function. It's called posterior EPRED. So it's going to predict back on the exponentiated scale. So it's going to get this to probabilities for us. It's going to predict the probability of these 3 guys making it to the Hall of Fame. We're going to turn it into a data frame, and we're going to set the names as the pitcher IDs. And the reason why is because when you use this function, R gives you the function really gives you the 4,000 potential universes for each of these 3 players, but it does so in this wider format where we see one column per player with 4,000 multiverses for each of those players. Okay, so let's try and summarize this a little bit. First things first, we can do some cool plotting of this. If we pivot everything longer, that's going to drop this into a long version where we have 4,000 rows per player, but stacked on top of each other, right? And we just want to plot the density of these and maybe even facet wrap it by player. I set scales to free because all of these guys are going to have different probabilities. So they're going to all shrink if we had the same scale for everybody. So probably if you're going to plot that, it's important to note that for people because they might look at these densities and
Oh, it's all the same.
yeah, draw inferences from it. The other thing we can do is we can use the apply function over the original predicted sample thing, because remember, it's one column per player. We can get the mean probability. We can get the standard deviation of the probability. Within the function there, we can also make this, call quantile with probabilities of 95%. So we have 95% quantile intervals. And then finally, we could also do things like, which is sometimes what we want to do when we make decisions, when we have distributions like this, is we might want to quantify the integral of the probability of being above or below certain thresholds. So for example, here we wrote in the function a little custom function that says, hey, take the observation for each of these columns, sum up the number of times in each of those 4,000 multiverses that we see a value that's greater than 0.02, so greater than 2%, and then divide by the length, divide by 4,000. So what we get returned here is the probability of each of these 4,000 players having their posterior estimates being greater than 2%. So you can see for the first player there, we didn't attach the names, so I don't know who that is, but there's basically a 0.2% probability density of that player having over a 2% chance of making the Hall. Contrast that to the second player. There's a 100% probability density that this player is a Hall of Fame type player based on their stats alone. And then the third player,
Well, greater than 0.02.
Sorry, greater than 0.02. Is it greater than 2%?
They have a 100% chance based on our models that they'll have a greater than 2% chance at making it
correct. Great, yes. That's right. The third player, however, he has a 38% of his probability density that we see in the plot there. He's the player in the middle in the green. 38% of that probability density is greater than 2%. So we can actually take that 2% line, and I don't know why we selected 2%. It was just a number looking at these players that we could put on there, and we can get a visual of that. So there we see the first player, who I think is Kevin Brown. We have all of his probability density is greater than 2%. Looks like he's, somewhere a little over 20% probability of making the Hall based on the peak of his distribution.
Mm-hmm.
We see that the middle player, who had 38% of that density, over 2%. And then we see the third player, who basically had it was a 0.0, it was like 0.2%. So very small distribution, or very small tail that's exceeding 2%.
Mm-hmm.
If we wanted to predict binary outcomes, so let's say instead we want to have a probability of ones or zeros, the threshold here is 50%, I believe, is the default. We do the same thing, but we just ask for the function being posterior predict, and this will just predict the actual ones and zeros. So now we have an actual, so like in the first universe, the middle player was inducted into the Hall of Fame. And then across the next 5, he was not. Whereas player 3 in the 5th universe, he was inducted into the Hall of Fame, but the others were all zeros. And in the first 6 universes, the first player did not have any values where he was inducted into the Hall of Fame. And we can summarize this as the mean of being over the being inducted into the Hall of Fame, which is basically the mean of our posterior predict universes where we were dealing with the probabilities. So there we basically see the exact same thing. And now the last piece is we want to make this prediction on the out of sample data. We don't have any ground truth for this, but Ellis, take us through that.
Sure thing. So we have our TBD data set, which are all the folks that either are just eligible this year or we're still waiting to find out whether they will or not be inducted. Excuse me, sans Peoples 2018. So this is all the people that have been eligible but still haven't been voted in.
Right.
So we can run this, and we're again selecting their player ID, IP outs, SO, R, and inducted. So we do have the ground truth. Well, I guess we do, but as in like they haven't gotten in yet. So we don't really need that.
Yeah, it's
Then
just NAs. Yeah.
yeah, or it's falses, I think.
Falses, sorry. Yeah.
Yeah. So then we mutate again on predict, fit Bayes, pass in our data set and say type is response again. So we generate our player pred TBD data set here. So, oh yeah, I guess they are NAs in inducted.
Yeah.
Um, then we say, okay, take this. We're going to take player ID, whether inducted or not, and then pred inducted. Again, arranging by the predictions and take ahead of those. So this player we've determined a 0.26% chance of getting into the Hall of Fame.
Jose
Or
Santana, maybe, and then Jake Peavy, Roy Oswalt, Tim Hudson, Billy Wagner, and I don't know the sixth player.
Burner.
I'm not sure who. Yeah, I'm not sure who that is.
Anyway, so this is people that this is the highest probability of somebody that has not gotten in but is still potentially going to be voted for. Is that so? Yeah, we'll see. They have yet to get in though, unfortunately for them. So we'll see. It seems like being a pitcher is not there's not a high likelihood of pitcher to get into the Hall of Fame if you are a pitcher to get into the Hall of Fame, unfortunately. So yeah, but what if you wanted to know for a specific player? Like, say you've got a favorite pitcher that you love, and you want to go, hey, what's the likelihood of them getting in given their current statistics that they've got? So you can apply this model to them as well, because this is just predicting what's the likelihood given their current career statistics that they get in based on innings pit or IP outs, strikeouts, and runs allowed. So being a Seattle boy, I not grew up, but saw Felix Hernandez play a number of times from a Mariners. And so he was always a lot of fun to watch. And so I was curious for the Mariners fans, is Felix likely to get in based on our model? So we can go. What's the process so you do that? So now we're now outside of our 20 minutes thing. This is just for funsies, but I think this is a really fun application of this. So let's figure out what Felix Hernandez's player ID is, which is Herna FE02. Now we can generate the data set that we did for all the other players by taking the pitchers post 1970, or we could just take pitchers realistically. It doesn't need to be post 1970. Filter for Felix Hernandez, group by player ID, remove ERA in BA because we can't calculate an average on an average. We summarize across some of these the values here and get the final season. So we apply all this.
You need the pictures.
Pitcher.
Mhm.
So let's not change it because we had it working before. There. We get Felix's career stats. So 169 wins, 136 losses, 419 games. So all his stats here. We can do is we can just throw this into our predict function and say, hey, type response. So with that, we get a 0.311 or 31% chance of Felix making it into the Hall of Fame. It's not low, not zero. Hopefully he does. I don't know. But we can also do that same exploration that we did for those three players for Felix. So we generate the posterior EPRED, taking fit Bayes and throwing in Felix's data set here. We get this long 4,000 row matrix. If we calculate the mean, again, we get that same value that we did, 0.311. We can get the standard deviation of 12.6. So there's a fairly high variability in Felix getting in. Get the quantiles. So 95th percent quantile is 54%, and the 5th percent quantile is 13.7%. Then we could get a sum of what are the total number of predictions where Felix gets in greater than 0.5, which is 8%. So in 8% of the universes, Felix gets in. Or 8.5% of the universes.
Yeah, so his true probability, we would believe, given his data, that his true probability of being a Hall of Fame pitcher is about 8.5%. At a 50% threshold. If the 50% threshold is a 1 or a 0, so 1 getting in or not, right?
Yeah. And so you, of course, depending on you could do some more exploration and actually determine our model just only needs to be 25%, and then oh, bumps up to 63.4% probability of it getting it.
Mhm.
It all, it just depends on how you look at it, right? But then we can also generate a histogram to look at the probabilities as well. So we'll use hist, drop in the epreds, set main, which is the title, to be King Felix Hall of Fame Preds. Set an AB line at the 0.5, set it to be red. Line width is 2, so it's a little bit thicker than the normal, and line type is 2. And let's do dev.auth. So we clear out what was there before. Now run that. So now we can visualize the probabilities of 0.05. So obviously the bulk of them are under 0.5. So the bulk of them not getting in if the cutoff is truly 0.5 for our model, not the number of votes. This is our model predicting it.
Yep.
But then it's not in the tail end like one of the players that we looked at earlier. It's
Mhm.
like solidly, it's not super high chance, but it's not
Yeah.
zero.
Yeah. No.
And so that is the probability of Felix making it to the Hall of Fame. Good luck. So with that, I think that's episode 173 of TidyX, how you apply Bayes to predict if a player is going to make it into the Hall of Fame. Next week, I think we've got a pretty cool potential way you might look at it too. So you should like and subscribe and ring the bell so you get notified when we post that next episode. With that, as always, my name is Ellis Hughes. You can find me on various social media sites at Ellis_Hughes.
Yeah, my name's Patrick Ward. You can find me on X at OSP Patrick at tidy_explained is where the screencast is on X. But YouTube channel, as Ellis said, like and subscribe, easiest way to get in touch with us and ask your comments and questions or suggestions. We do have a Patreon page if you'd like to donate to the show and support us. We're grateful for anything that you would like to give.
Thank you all so much. Keep on exploring your world.